Welcome to this explainer. If you've ever stared down a Cambridge IGCSE Additional Mathematics past paper, you know the vocabulary can sometimes hit you like a ton of bricks. It's almost like trying to read a completely foreign language, right? The glossary is absolutely packed with dense, intimidating terms. But today, we're stepping into the training dojo. We aren't just going to memorize a dry alphabetical list. No, we're going to completely demystify this language by grouping these critical mathematical terms into logical, interconnected universes. By the end of this, you'll be able to adapt your style to any question that comes your way and flow like water through your exam. So let's dive right in.
Rather than a boring A to Z read-through, we're going to navigate this glossary conceptually. We will move systematically through 5 essential stages: functions, algebra, calculus, kinematics, and finally, sequences. Let's start with Section 1, Functions, the mathematical machines. Okay, think of a function as the absolute fundamental processing machine of mathematics. By definition, it's a rule that associates each element of one set, your input, with only one element of a second set, which is your output. But what does that actually mean for you in an exam? It means it's a precise, highly predictable operation. You feed a very specific input into this machine, and it mathematically transforms it into one singular output. It is a strict rule follower. Everything else we build today relies on these exact machines. Now, to truly master how these mathematical machines work, we have to actively contrast what goes into them with what actually comes out of them. So your domain is the entire set of all possible inputs you can safely feed into the machine. On the flip side, we have the range, which the Cambridge Glossary also beautifully calls the image set. This represents all the possible output values that the machine can spit back out at you. Input is your domain, output is your range. Simple as that. And within this universe, we run into a highly specialized, absolutely perfect machine called the 1-1 function. This is a function where every single object has a totally unique image, and every image comes from only one object. It perfectly pairs inputs to outputs without any overlap. Because it's a flawless two-way street, its effect can be completely reversed by what we call an inverse function. Oh, and before we unlock our next mathematical universe, I want to quickly remind you, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button right now so you don't miss any of our strategy guides. All right, let's move on to Section 2, Algebra and the Polynomial Power. Building directly on our understanding of functions, we can start organizing polynomials kind of like Russian nesting dolls. You see, polynomials are expressions made up of positive integer powers, and they're organized by their order, which is simply the highest power of the variable in that expression. And they scale up so gracefully. We start with simple linear equations, where the order is just 1. Then we step up to quadratics at power 2, cubics at 3, quartics at 4, and all the way up to those complex quintics with a massive order of 5. So, looking at those absolute algebraic giants, the complex quintics and quartics, you really have to ask yourself, how on earth do we actually break down and solve these equations? How do we find their roots? Those exact x-coordinates where the curve physically touches or crosses the x-axis. Well, in our exam toolkit, we rely heavily on 2 core foundational theorems. The first one is the factor theorem. The rule states, if x minus a is a factor of f of x, then f of a equals 0 and x equals a is a root of the equation. In plain English, this theorem is an elegant, direct shortcut. If you know a specific expression is a perfect building block, a factor, of your polynomial, then plugging in that exact value gives you a result of 0. No remainders, no leftovers. Boom, you found a root. But what happens when things aren't perfectly clean? That brings us to its essential sibling, the remainder theorem. This rule says that for any polynomial f of x, f of a is the exact remainder when f of x is divided by x minus a. This is an incredibly powerful tool. Instead of doing long, painful algebraic division during a timed exam, this theorem calculates exactly what is left over when the division isn't perfect, just by substituting a single value into the function. It's a massive time saver. Let's transition to Section 3, Calculus, the art of change. Mastering those static algebraic curves naturally pushes us into the dynamic, continuous study of change. Calculus is essentially governed by 2 opposing, yet deeply interconnected forces. On one side, we have differentiation. This breaks things down to find the derivative, or the gradient function. It tells you exactly how fast something is changing at any specific instant. On the other side, we have integration. This does the exact reverse. It builds things back up, using that rate of change to find a total accumulated value over a specific interval. Now, here is a crucial exam strategy tip. When you are doing that build-up process, integration, you absolutely must distinguish between a definite integral and an indefinite integral. A definite integral has two specific limits or boundaries. You are evaluating the area between point A and point B. An indefinite integral, however, has no limits, and because those exact boundaries are missing, you must remember to add that arbitrary constant of integration, your plus c. Examiners look for that, so don't lose easy marks there. Let's put this into a real-world exam scenario. Here's a classic question. How do we find the exact turning point of a curve? By using the raw power of differentiation, we can analyze a curve's gradient function to figure out the precise mathematical moment it stops going up and starts going down, or vice versa. By calculating exactly where our gradient hits a flat zero, we locate what is called a stationary point. Now, this could be a standard turning point like the absolute peak of a hill or the bottom of a valley, or it could be a point of inflection, a really fascinating spot where the curve shifts its concavity from up to down, but doesn't actually turn around. Hey, stop scrolling for a second. If you're finding this breakdown helpful, remember to subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've got so much more to cover, so let's keep going.
Moving right along to Section 4, Kinematics, the math of motion.
Applying all those rules of calculus directly to physical, real-world spaces plunges us into kinematics. But listen, before objects can even start moving, we have to establish exactly how we are measuring them. You need to intimately know the difference between a scalar and a vector. A scalar is a simple quantity that only has magnitude, like basic speed or distance. But a vector crucially adds a specific direction. So in this mathematical universe, distance becomes displacement, and speed becomes velocity, because we now care entirely about where that object is physically heading.
Motion actually tells a sequential, highly logical mathematical story. Step 1. An object begins with displacement, its distance from a start point in a given direction. Step 2. We differentiate that displacement to find its rate of change, which becomes its velocity. And step 3, we differentiate that velocity to find its rate of change, and bam, you arrive at its acceleration. It's a flawless, 3-step chain of mathematical logic.
Finally, we arrive at Section 5, Sequences and Series, Predicting the Pattern. Stepping out of physical motion, we enter the universe of infinite mathematical patterns. It is absolutely vital to separate two concepts that trip students up all the time in exams: a sequence versus a series. A sequence is merely the ordered set of numbers themselves, just the individual terms lined up in a row. A series, however, is the actual mathematical summation. It's the total value you get when you physically add all the terms of that sequence together. Sequence is the list, series is the sum. Keep that straight, and you're golden.
These order patterns generally behave in two very distinct ways. First, we have the arithmetic sequence, where terms grow or shrink by adding or subtracting a fixed amount every time. We call that the common difference. Then we have the geometric sequence, which is much more explosive. Here, the terms change by multiplying the previous term by a fixed number, which is known as the common ratio. When you're analyzing these geometric series, especially the infinite ones, your main goal is to identify their long-term behavior. Are they convergent or divergent? If the terms are progressively getting smaller and smaller in size, eventually settling towards a specific limit, it's a convergent series. But if those terms are progressively getting larger and larger, expanding outwards infinitely, that is divergent. And as you start pulling elements from these sets to build arrangements, always remember this golden rule of counting: permutation versus combination. In a permutation, it is an ordered arrangement, meaning the specific sequence or order dictates absolutely everything. But in a combination, you're just making a selection from a group. The order simply does not matter at all. We have traveled from the basic machines of functions through the heavy structure of algebra into the dynamic shifts of calculus, the motion of kinematics, and finally, the infinite patterns of sequences. Now that you've got these foundational languages unlocked, what new mathematical universe will you decode next? Practice these concepts, adapt to the questions, flow like water in your exams, and you will absolutely crush it. One final reminder before we go. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Drop a comment below with your target grade and the biggest challenge you're facing. Thank you for joining me in this explainer, and I'll see you in the next one.